In the last several videos, we've introduced valence bond theory and the concept of hybridization. In this video, we're going to apply that valence bond theory to ethane. So ethane is an organic molecule. It has all single bonds. You have 2 carbon atoms in the middle, and each of those carbon atoms has 3 hydrogen atoms attached. That means that each of those carbon atoms has a total of 4 electron groups around it, making it tetrahedral. And that means that those carbon atoms can be described as being sp3 hybridized. Now, of course, the picture I drew at the top of the page does not show the correct geometry for the molecule. This beautiful computer-generated picture in the middle shows you that. Now, if I wanted to draw it myself, then since I can't do lovely perspective like the computer did there, what I'm going to do instead is use wedge and dash notation to show which groups are coming toward me out of the page and which groups are going away from me into the page. So I start by drawing the atoms that are flat in the page, the ones I've just highlighted here. So we have our 2 carbon atoms and 2 of the hydrogen atoms, and those all fall along the plane of the page. Next, I indicate which atoms are coming toward me using a wedge. I'm essentially trying to draw the bond with extreme perspective. That's what that convention means. So this wedge here, a nice colored in triangle, indicates that that hydrogen is coming toward me out of the page, and the same thing is true for this hydrogen over here. The way that we show atoms that are behind the page or the bonds going away from us is using a dashed wedge. So essentially a series of dashes that get longer as you get away from the central atom. And we do that for our 2 hydrogens here that are going away from us into the page. And so that's how I would draw a 3-dimensional picture of ethane. Now, when you're doing the wedge and dash notation, it doesn't matter exactly how you've rotated the molecule around. It does, however, matter what the relative positions are of the 2 straight lines versus the wedge and the dash coming out from that central atom. It is okay to have your 2 straight lines like that and your wedge and your dashed line going down instead. And please don't connect those dashes. If you do a squiggle, it means something completely different. So they do need to be distinct dashes. That's fine. I could draw it sideways like this and have a wedge and a dash, and that's fine. But you must always have the 2 straight lines next to each other and the wedge and the dash next to each other. If you were to draw something that looked like this, where you go straight line and then wedge and then straight line and then dash, that is not okay. That does not show tetrahedral geometry. It actually shows square planar on a really funky angle. So the key thing with wedge and dash notation, make sure that the wedge and the dash are next to each other. And after that deviation, let's go back to valence bond theory. So we've established that each of the 2 carbon atoms is sp3 hybridized, and that means they will each have 4 sp3 hybrid atomic orbitals. The valence atomic orbitals for the hydrogen are, of course, the 1s orbitals, so those are the orbitals that we'll be combining to make the bonds. If I want to show my bonds, show what I'm doing in terms of valence bond theory, I have to, of course, start by drawing out my molecule, so I'll go ahead and do that using that wedge and dash notation that I talked about on the previous page. My wedges and dashes aren't always the prettiest things ever, but I try. So this bond here in the middle between the 2 carbon atoms, since each carbon atom is only bonding using an sp3 hybrid, must have been made from an sp3 hybrid orbital from each of the two carbons. And because those hybrid orbitals are pointing directly at each other, this is going to have to be a sigma bond. So we would say that this is a sigma bond between one carbon using an sp3 hybrid orbital and another carbon also using an sp3 hybrid orbital. And that's how we would describe the bond if we're just asked to describe it rather than actually drawing the full out shape. You'll notice that because it's a sigma bond, because if I were to draw it out, it would look kind of like this, with a little tail on the back of each end. You can spin around either atom and your orbitals still have perfect overlap. And so single bonds you can rotate freely around. If you start playing with a molecular model kit, which you'll definitely want to do if you take organic chemistry, but if you're planning to take organic chemistry, you might just want to get one now and start playing with them for the organic section of this course too. You'll see that anytime you have a single bond, the model kit will let you spin around that, no problem. And that's because a single bond is just a sigma bond. And that's true whether you're talking about the molecule from a molecular orbital perspective or whether you're applying this valence bond theory to it. So that takes care of the carbon-carbon bond. The other bonds in the molecule are all equivalent to each other. They are all carbon-hydrogen bonds. Those are also sigma bonds. Every bond in this molecule is actually a sigma bond. And each of them is made by taking a carbon atom using the sp3 hybrid orbital and combining that with the 1s orbital on the hydrogen. And the notation that you're seeing me use, listing the type of bond and then the orbitals used to make it, is a nice clear way to describe a bond in cases where you're not actually asked to draw it. And you'll see it in the answers to all the problem sets. And of course, all 6 of these carbon-hydrogen bonds can be described in the same way. If I was writing this up properly as an answer key, solution set, writing a test, something like that, I would explicitly label each of them. But since this is a video and you don't want to sit through me writing the same thing 6 times, I'm just going to say times 6. And that's the valence bond picture for ethane. It's straightforward. You follow this process of draw the Lewis diagram, assign the Vesper geometry, assign the hybridization,